So, in the last video we were discussing about properties of Hermitian matrices. In this video we will try to prove the properties of these Hermitian matrices. Hermitian matrices are also called skew symmetric matrices, okay. When the entries are complex numbers, these matrices are called skew symmetric. When the entries of this matrix are real, then it is a symmetric matrix. So, you have beautiful properties for the symmetric or skew symmetric matrices, that all the eigenvalues are real and you have corresponding n number of n linearly independent eigenvectors you have. You can make them orthogonal once you have these eigenvectors, and they form so because they are you are in the n dimensional space. Any vector, any n dimensional vector, you can write in terms of these n linearly independent vectors which are orthogonal. So, we will see one by one all the properties that we listed in the last video. So, we will just try to prove them, okay. So, before I do that, so we will just see the definition of skew symmetric or symmetric. You can put it in a different way, more general way, okay. So, we will see that. So, let us put it. So, what is a skew symmetric? Skew symmetric matrix, skew symmetric matrices or Hermitian matrices, skew symmetric or Hermitian matrices. So, the definition is, what we know is a n by n matrix is Hermitian if this is the definition, okay. So, you have A bar or A transpose of it, and you take a bar is actually is A itself. So, this you can call it A star. So, star denotes transpose and bar, okay. So, if this is the case, if A star equal to A, then you say that it is a skew symmetric matrix. So, the same thing you can put it in a different way in an equivalent form, but it is more general, is if you take the dot product with you have as you operate this matrix A on any vector x, and then you take a dot product with another vector y, okay, in Rn, okay, and this should be same as x, you bring this A here. So, if you bring it here, that should be same. So, if I can put A acting on y and you take the dot product with x, if this is the case, okay, so you can also say A is Hermitian, if this is true, this equality is true for every x comma y in the vectors. For all vectors x and you take any x y, this is true, then this is actually same as saying A star equal to A. So, with this definition we can prove the properties for a Hermitian matrix or skew symmetric matrix. So, first property we will try to prove the properties, okay. Proof of properties 1. So, what is that? All eigenvalues are real, all eigenvalues are real. So, how do I prove this? So, what is the eigenvalue? So, let lambda be an eigenvalue. If you have an eigenvalue, what is the meaning? Definition of an eigenvalue is there is a non-zero solution, some v, okay, v non-zero, such that A v is actually equal to lambda v, okay, for some non-zero v belongs to Rn. So, that is the meaning. If you have lambda is an eigenvalue, that means you have a non-zero solution for the system A minus lambda I into x equal to 0. So, the solution is v. For some non-zero v if you have, then you say you have this is an eigenvalue and V is the corresponding eigenvector. So, how do I show that? So, what we do is all the eigenvalues I want to show it is real. So, you consider so given that A is Hermitian. So, this is AV into V. Okay. So, this if you consider this is equal to, because AV is now lambda V. So, lambda V into V. So, this will give me, so lambda is a constant. So, you can take it out. So, as a lambda. So, what is the definition of this dot product? Dot product is I is from 1 to n lambda V I, okay, into V I square, right. So, this is what is the meaning. So, this is equal to lambda comes out, you have I is from 1 to n V I into V I. So, this is actually gives you lambda into, this is now dot product of V and V. Okay. Now, you consider, now this is same as, now if you can see that this is actually same as, because A is Hermitian, now I use this definition of Hermitian, V into V dot product with AV, both are same because A is Hermitian. Now I replace AV with lambda V. So, you have V lambda V. Now, this this product is, sorry, this you have bars. Okay. So, you have bars, I is from 1 to n and you have V I dot product with lambda V I bar, full bar. So, that will give you lambda bar comes out, what you have is I is from 1 to n V I dot with V I bar. So, this is nothing but lambda bar of dot product with V. So, these are same. So, this implies lambda my lambda. So, what you have is all are same, right. You can see that these all are same. So, lambda V V is equal to lambda bar V V dot product. So, you know that this is a non-zero V. So, this cannot be, this means this is simply non-zero, this is non-zero quantity. So, we can cancel, if because it is non-zero quantity we can cancel, that will give me lambda equal to lambda bar, that means lambda is real. So, if you take any eigenvalue of a Hermitian matrix, then eigenvalue has to be real. What happens to the eigenvector? So, you can make them are so eigenvectors, let eigenvectors of a Hermitian matrix has real entries. How do I show this? You can make them. Okay. So, eigenvectors of a Hermitian matrix, you can make them to have real entries in it. So, they have real entries in it. So, how do I show that? So, you say lambda is, suppose the lambda is an eigenvalue, correspondingly you have an eigenvector, let us say V. Okay. So, let V be an eigenvector corresponding to an eigenvalue lambda. So, there is always correspondence. If you have eigenvector, there is corresponding eigenvalue lambda. Okay. If you say something is some value is an eigenvalue, that means there is a non-zero solution vector, that is called eigenvector. Okay. Satisfying A V equal to lambda V. So, if you have an eigenvector, so what you have is immediately lambda V, A V is lambda V. Okay. Suppose V is complex. Okay. So, let us say complex eigenvector. Assume that lambda V is having complex vector, complex complex eigenvector. Then you can take a bar. Okay. What happens to V bar? V bar AV bar. So, AV bar equal to lambda bar V bar. So, I just take the bar for this. Okay. If you take a bar and I know that A is having real entries. So, you consider all the matrices with real entries, okay, that are skew symmetric. So, this is our as a real Hermitian matrix, real Hermitian matrix. So, this property is it is not true for if A is having complex entries. If A is a matrix, Hermitian matrix, that means for skew symmetric matrix, okay, if A is a skew symmetric matrix with real entries, that means A is symmetric matrix. For a symmetric matrix, you consider all the eigenvectors. So, if the eigenvector is complex, you can actually make them real, okay, that is what we are showing. So, if you consider eigenvectors of a real Hermitian matrix, okay, that means basically symmetric matrices, you can say symmetric matrices of a symmetric matrix, symmetric matrix have real entries in it. So, let us consider a non-zero, so be an V be an eigenvector corresponding to an eigenvalue lambda. So, you have this, that means this implies this. Now, we assume that V is a complex eigenvector. Now, if I take this bar, so what happens? This implies because A is a real symmetric matrix, that means A is real, A is having real entries. So, this simply A V bar equal to lambda bar V bar. So, that means, and this is the same as, but I know that if it is a symmetric implies this is a Hermitian also, okay, just by the property 1 and the lambda is always real. So, this lambda bar is actually lambda V bar. So, what you found is A V bar equal to lambda V bar. So, if V is non-zero eigenvector, because it is an eigenvector it is non-zero, V bar is also non-zero. So, that implies V bar is also an eigenvector. Okay. So, you have two eigenvectors corresponding to, if V is complex eigenvector, V and V bar are linearly independent. Okay. So, if x plus iy, x minus iy, you take a division, if y is non-zero, if you take the division, that cannot be a constant. Okay. So, they are linearly independent vectors. So, you can easily see, right. So, x plus iy is here, x plus iy, x minus iy is x is same, y is here, so somewhere here. So, these are two linearly independent vectors. So, this is also an eigenvector. So, now what I choose is you have two eigenvectors V and V bar. What I do is I consider their sum and then I consider their difference, divide by 2i, you take the half, okay, that is a real part of V, and here these are imaginary part of V. V minus V bar divided by 2i. Okay. So, if we choose this, if V and V bar are linearly independent, real part of V and imaginary part of V, this is the sum and difference are also linearly independent, since V and V bar are linearly independent. If they are complex, yes, they are linearly independent. So, that means if you have an eigenvalue corresponding to a symmetric matrix, so it may have a complex, if it has a complex eigenvector, that means a bar is also eigenvector. So, that means it has two eigenvectors, two linearly independent eigenvectors corresponding to the lambda, and you take the real part and imaginary part, they are also linearly independent. So, what you have is real part of V, you call this V1, okay, and this is V2. V1 and V2 are eigenvectors of A corresponding to lambda. Okay. And you see that V1 and V2 are having real entries. These are all real eigenvalues, real eigenvectors. That is what you have seen. So, if you have a symmetric matrix means that is also Hermitian. So, you have a real entries. So, A bar A transpose bar equal to A. So, bar does not matter, right, because you have a symmetric matrix, that means real entries. So, that means this Hermitian from the property 1 you see that the eigenvalues are real. Corresponding to that one real eigenvalue, any eigenvalue, you have let us say complex eigenvector. So, then its bar is also an eigenvector. So, you have two nearly independent eigenvectors, and you take the real part, implies immediately real part and imaginary parts are also linearly independent. So, that implies they are the real eigenvectors of A corresponding to the eigenvalue lambda. That is what is the property 2. So, you see that if you have a symmetric matrix, if you have a matrix with real entries and it is symmetric, all eigenvalues are real, corresponding eigenvectors are also real eigenvectors. Okay? That is what you have seen. So, another property which we have seen earlier, what are the things we have? So, this is what we have seen, distinct eigenvalues, eigenvectors of eigenvalues are distinct eigenvectors if eigenvalues are all distinct. So, that is clear, second property, that is easy to see. Okay. Let V1 that lambda 1 lambda 2, lambda 1 is not equal to lambda 2, okay, are distinct. Then distinct eigenvalues. Okay. Immediately from the definition of eigenvalue, A lambda A V1 corresponding eigenvectors A V1 equal to lambda 1 V1 and A V2 equal to lambda 2 V2, because V2 is corresponding eigenvector. Okay. V2 is an eigenvector corresponding to the eigenvalue lambda 2. So, I want to show is given that lambda 1 is not equal to lambda 2. Okay. So, I have to show that V1 is also not equal to V2. So, how do I show that V1 is not equal to V2? So, what you do is, because lambda 1 is not equal to lambda 2, lambda 1 minus how do I show that eigenvectors are all suppose. Okay. So, let us say suppose V1 equal to V2, then what happens? A V1 equal to A V2, which is equal to A V1 is, I already know that lambda 1 V1, okay, which is equal to lambda 2, A V2 is lambda 2 V2. So, what does it mean? So, because now V1 equal to V2, right. So, V1 equal to V2, so both are same. So, this is same as lambda 2 into V1. Okay, so lambda V, because that is what we assumed. If you assume and this is true, right. So, if you consider these two, it implies you have lambda 1 V1 equal to lambda 2 V1. V1 is an eigenvector which is same, so non-zero. So, you can cancel both sides, that will give me lambda 1 equal to lambda 2, but we know that given that it is non-zero, they are not same. So, that means in a contradictory way we can show that eigenvectors are also different. So, that means this assumption is wrong. This is a contradiction to the assumption that V1 equal to V2. So, that means V1 cannot be equal to V2. So, this is how you see the property here which we listed in the last video. The distinct eigenvectors you will find corresponding to distinct eigenvalues. Okay. And you can also show that they are orthogonal corresponding to corresponding eigenvectors, distinct eigenvalues. Let us say you have distinct eigenvalues. So, this V1 and V2 are orthogonal. So, I want to show that V1 V2 are orthogonal for, let us say, right, let lambda 1 is not equal to lambda 2 be distinct eigenvalues. Then the eigenvectors V1 and V2 are orthogonal. That means the dot product should be 0. So, how do I show this? So, these are just write the definition of eigenvalues and eigenvectors. So, V1 is eigenvector corresponding to lambda 1. So, implies AV1 equal to lambda 1 V1, and V2 similarly you have AV2 equal to lambda 2 V2. This is what you have. Now, I consider what I do is I consider AV1 V2, okay, this dot product if I consider, okay, consider this by definition, because A is Hermitian, okay, and I do not say that it is real symmetric, that means it is actually Hermitian. It may have complex entries, A may have complex entries. So, by definition this will give me V1 AV2. Okay. Now, what is this left hand side? Left hand side is actually equal to, this is equal to AV1, I can write lambda 1 V1 V2, which is equal to this I can write V1 AV2 is lambda 2 V2. Okay. Lambda 1 lambda 2 are real, that we already know, okay, distinct eigenvalues of any eigenvalue is real for a Hermitian matrix. So, these are real. So, if you write this, so if it is here, if it is a real, if it just comes out lambda 1, you can just verify, make a dot product make a dot product and take this lambda 1 out, what you get is V1 V2. Here if the value is here, this will come out as a bar, because it is a real, no issue. So, you do not have problem here. So, you do not even, so when it comes out bar, because it is real, it is same as lambda 2 into V1 V2. Now, V1 V2 are eigenvectors, so they are non-zero. If they are non-zero and lambda 1 is not equal to lambda 2, so that implies lambda 1 minus lambda 2. So, this is same. So, this into this dot product V1 V2 has to be 0. Now, this cannot be 0, okay, because lambda 1 is not equal to lambda 2. So, that means V1 V2 has to be 0, dot product has to be 0, implies V1 V2 are orthogonal. This is how you show, okay. So, you can just remember, if any distinct eigenvalues corresponding eigenvectors are always orthogonal. If they are not orthogonal, that is possible when they are not distinct. So, when they are not distinct, when the eigenvalues are not distinct, that means you have a repeated eigenvalues. When it is repeated m times, you have m linearly independent eigenvectors, okay, that we do not show, it is not that simple. So, you can assume that. So, if it is repeated m times, you will have m linearly independent eigenvectors. So, those you can make, those m vectors, they are linearly independent and you can make them orthogonal by the Gram-Schmidt process, which I explained in the last video, okay. So, with this we will try to imitate the whatever properties we have for this Hermitian matrices. We will just take second order homogeneous equation, okay. Let us start with the second order homogeneous equation. So, let us consider this, we will imitate whatever we have, okay. So, if we have A naught of x, this is what we have, A naught of x y double dash plus A1x y dash plus A2x y, okay, and then you include some parameter lambda, okay. So, because we are dealing with this eigenvalues, okay, Ax equal to A, earlier you have for the matrix Ax equal to lambda x, right. This is what you look at if you want to see where something, whether you have a non-zero solution for for this x. If there is a non-zero x, then lambda is an eigenvalue. Okay, corresponding x, that non-zero solution is eigenvector. So the similar lines we consider the equation. So you have considered a minus lambda I as a matrix. Okay, this is what we consider. So the same way, when you consider the homogeneous equation, differential equation also, what we do is this is where it normally ends, this is the differential equation. So I want to consider this kind of equation. So you include a parameter lambda. So lambda y. So if you say lambda a3 of y, okay, a3 of x into y equal to 0. So this is the general second order equation which is of this type, okay, analogous to the matrices, matrix operator. So this is a matrix operator x equal to 0. I have this differential operator, okay, m of y is this, rather m plus lambda a3 of x. So this is what is your a minus lambda x, okay. So let us write this m plus lambda a3 of x acting on y. So where m is actually defined as a naught of x d square by dx square from this term plus a1x d dx plus a2x, that is it, right. So that is your my. So if you put y here, that is actually these 3 terms, and plus lambda a3y is as it is. So that is equal to 0. So that is the equation. So I can always put this in the form of in the Hermitian form. So let me see what that Hermitian form Ly. I make this as, I will put it in a nice form. So that is called the, what I do is I will try to put this in this form Ly equal to some lambda y. So this I transform, okay, I bring it into, transform into this type. So that this is like Ax equal to lambda x, okay. So this is a general equation, this is a general equation. So if it is a matrix, directly you have already in this form, both are same, this is already symmetric form. If A is a general matrix, you all the properties, so A is not, if A is a general matrix, though it is in this form, it is not symmetric, it is not symmetric, A is not symmetric or A is not skew symmetric. Given that A is skew symmetric, it is already in this form, okay. So in the infinite dimension, for the differential equation, what happens, though you consider the, say A is the general matrix, so I try to put Ly equal to lambda y, L is the operator, L is like a matrix here, and along with some boundary conditions I make this L is Hermitian, okay. So here for the matrix you do not have any boundary condition, there is nothing. So you A is Hermitian means A star equal to A, okay. If you know that A star, so you put it, that then you have all the properties. But for this equation is already in this form, so you first in this put in this form, then you show that L star equal to L. I will tell you what exactly it means, okay. This is actually symmetric provided with some boundary, provided you have some boundary conditions. So that means y is a y of x, right. So y is actually y of x, so x belongs to some domain A to B, finite domain, okay. So you have boundary conditions at A and B, okay. So we will see that. So how to, first of all we will try to put it in this form Ly equal to lambda y. So Ax equal to lambda x for general matrix A. So first we write this way, okay. So Ly equal to lambda y. So but you see, if you consider equation like this, it is not proper, so it is not in that form Ly, see it is not Ax equal to lambda x. You try to put it as Ly equal to lambda y. How do I do this? You simply divide with, assume that A naught of x is non-zero, okay. So assume that A naught of x is not equal to 0. Why I assume this? If it is 0, it is not defined at that point, so it is not in the domain, part of the domain, okay. So you can always assume that it is non-zero in that domain. So it can be even at maybe at A and B you may have A naught of x is 0. So the domain I always consider as open interval, okay. So, I always consider as open interval. So, I assume that this is true for every x in the open interval a to b. Then I can divide it a naught. If you do that, y double dash plus a1 by a naught y dash plus a2 by a naught into y plus lambda a3 by a naught to y equal to 0. Okay. So, this implies, now what I do is I try to put this together. So, if I try to, how do you put this together? You have earlier you have seen y dash p of x y equal to 0. You want to write this as a ddx of something. What you do? You multiply some integrating factor. So, what is integrating factor is e power integral px dx. So, you do that. So, if you multiply this integrating factor, so let us call this, let p of x multiply p of x, I call this p of x as e power integral integrating factor, I am calling here it is p. Okay. So, this is actually a of x you say, then you have integral a of x. So, this whole thing I am calling px. Okay. So, let us px as a1 by a naught into dx. Okay. Then if I multiply this, you have px y double dash plus a1 by a naught into px y dash plus a1 by a2 by a naught into px y plus lambda a3 by a naught into px into y equal to 0. That is what if I multiply. Now, I can put this together as 1. So, that is y dash into px. For this you differentiate ddx of, if I write like this, ddx of dy by dx. So, what if you see this px into, you differentiate this part px into y double dash first term, second term px into y dash, you have to differentiate p. If you do, because p is e power this, e power itself, that is p, and you differentiate a1 by a naught comes out. So, that is what he says. So, these two terms I can put it like in this form plus whatever here, this you call it some q of x y equal to plus, and then plus lambda some w of x, this you call it w, this is q, this is w of x into y equal to 0. Okay. So, this is what I have. So, now I can write this nice form. So, Ly equal to lambda y. Okay. This is like you can put it in that form. So, this means this you can write minus ddx of px dy by dx, okay, plus qxy, okay, this is minus equal to lambda wx y. I take this, that is left hand side. So, you also divide this with the wx. So, you have 1 by wx equal to lambda y. This is x belongs to AB. So, the domain is this. So, this is now nice form. So, this is your Ly equal to lambda y, where L is minus 1 by wx, L is this operator, this is like a matrix. Okay. So, you have ddx of px ddx plus qx, this is just an operator, you can act on any function y. Okay. So, this is what is your matrix, it is like in this form. So, I want to see when L is Hermitian. The question is when L is Hermitian. What is the Hermitian meaning? I want to make the dot product. So, with any, so is Hermitian if I work with some functions. So, you have a functions here, earlier we have vectors, now y of x is a function. So, I have a function L f g, f g are two functions. If This is the definition of Hermitian if this is what is true. So, F L G, if I bring this here, okay, for every, this is true for every f x g x, okay. So, earlier you have vectors, now we have functions. For every functions this is true. So, you just what is this dot product. So, you define this dot product now. So, this dot product in this case for the functions is we can define the dot product. So, I define this dot product of f g, okay, is, so is depends on this L. This actually this dot product is not usual one, that is as a summation, because you are involving with functions, you integrate. Earlier dot product with V 1 and V 2 is simply summation, I is from 1 to n, V 1 I. So, let us say u v, so you have u I into V I bar. Now, what you do is you do the same thing here. So, what is the domain? So, you are doing it earlier from, because only finitely many elements u 1 u 2 u n, v 1 v 2 v n, each component you multiply. Here also you do f x into g x bar, and x is between, x is continuously running from a to b. So, you integrate. So, your addition is like integration, a to b f x g x bar dx, okay. You see that, and see when so when you have in the L, when you have this W, this inner product, the inner product you sorry, when W is non-zero here. So, you can see that in the operator L, W, what is this W? W is actually A3 by A naught into Wx, right, A3 by A naught into Px, which is, you can assume always that it is positive, okay. So, we will see this is always assume that is non-zero, okay. So, assume that, we can assume that this W is, so because you divided, right, so divided means you assume that if W of x is non-zero, whenever you divide it, you should that should never be 0, okay. So, you have such a WF. If you have, what we do is I have this Wx into f into g. So, you have a weight function, this is called the weight function, okay. So, the in the dot product you have a weight function, if it is 1 it is the usual dot product in for the functions, okay. So, this is the definition, you define the dot product whenever you have when your differential equation is having in this form with L where 1 divided by the W, whatever W you divided, that should come here, okay. With this definition, okay, we define the dot product, we define this dot product. So, with this dot product we apply here, with this you want to see whether it is Hermitian or not, okay. So, you have actually you have to define this first. So, let us write, let's do this first in a logical way. So, once you have this operator, Ly equal to lambda y, I define the dot product. What is the dot product here? Dot product as for the functions f(x) and g(x) as a definition. So, earlier dot product means a product of sum of the products of each components of a vector. So, now you have f(x) into x u fix f(x) g x bar, okay. This is the component and you are doing it over all x which is in a range in the interval a to b. So, it is continuous. So, you have to integrate from a to b, and you have, because for this L, once you see that this operator is having this W which is non-zero, the W is called the weight function that should be there in your dot product. So, that is how with this dot product I define this dot product, this is the with this dot product I want to see whether L is Hermitian. Okay. Check if L is Hermitian with respect to this dot product, the above dot product. Okay. With this dot product you want to verify. So, what is the meaning of L is Hermitian? You have L, F, G, you want to verify this. Okay. F, L, G for every F and G, Fx and Gx. Okay. This is what you want to check. Okay. So then only this operator L, is differential operator L is self-adjoint, just like in your matrices. A is Hermitian, means A star equal to A, you can directly check with your matrix. Okay. So, that is the same as saying earlier we defined A x equal to y equal to x A y, that is the definition we have given. So, both are same, equivalent. So, you want to verify this, you start with the left hand side. What is the left hand side? You write A to B Wx L f x and G of x bar dx. Okay. So, this is equal to, what is this one? So, A to B Lf, you can write like Lfx Wx Wx G bar of x dx. You can now define what is your Lf. Lf is, you can use this one. So, this you write it. So, that will give you A to B minus comes out Lf, I am replacing 1 by Wx Px, there is a Px f dash of x for this whole dash. Okay. So, if you want to nicely you can write ddx of Px df by dx plus qx into f of x. You acting, so acting L acting on f, this is what is your Lf into Wx Gx bar dx. So, this is equal to minus A to B, this W goes now. So, what you are left is simply ddx of Px df by dx plus qx fx into gx bar dx. Okay. So, we will see the left hand side is actually right hand side, you want to see that. Okay. So, we will see exactly what is the left hand side and when this left hand side is, so we will just show. So, we will see this. So, we started with the left hand side that we defined here. Now, we just use the integration by parts in the next video and see at right hand side plus certain terms you will get, we will make that when you, so you have to define, you want to see that is actually left hand side is equal to right hand side, when the left hand side is equal to right hand side. So, you need to impose certain conditions, okay, for the differential equation. So, you need to give some boundary conditions. So, once you give the boundary conditions, you can see that left hand side will be equal to right hand side. So, then it will be Hermitian operator. So, once you have the Hermitian operator, all the properties which you have seen for the matrices will be valid here. So, we will just use directly analogically, okay, and then we see this in the next video.